And we're back. Welcome back from your weekend. Today we will continue our conversation about the link layer, and our focus today will be on link layer switches as well as virtual LANs and possibly introduce data center networking. But before we get started, let's look at some administrative bits. As you all know, written exam number 2 will be at our class meeting on Thursday, the 23rd of April, this Thursday at 12 noon. It will be a 28-hour take-home exam, so it will be due on Friday, the 24th at 4 p.m. So please note and make sure you pay attention to this due date and time. It is not at the usual 11:59 seconds that I usually have typically for assignments. This is an exam. Please make sure you are not late. Manage your time accordingly. It is 28-hour. You are free to use materials that you find useful to you, but this is to be an individual effort. With privilege comes responsibility. So this is no collaboration. You'll be asked to sign an honor statement. And if there is evidence of cheating and collaboration, all parties involved will receive a 0, no questions asked. I'll just put a 0 for everyone. So please make sure that you note these dates, a 24-hour take-home. It will be released at class period. We will spend time going over the questions, and I can answer your questions as well. Okay, so let's continue on. Last time we left off with different Ethernet standards for the physical layer, and depending on the type of physical layer, we had a different name for the cabling. And so now we'll continue on with Ethernet switches. Now, these Ethernet switches are link layer devices, so they're sometimes called layer 2 devices, and their responsibility is to store and forward Ethernet frames. So in that regard, it acts a little bit like a router, but there's a very important and key distinction here when we talk about link layer switches. The biggest distinction here, you'll notice it says store and forward frames, right? That's not datagrams, which is a layer 3 notion. It's frame, which is a link layer notion. And so what happens? These switches examine an incoming frame's media access controller MAC address, and then based on that MAC address, it selectively forwards this frame to one outgoing link, Ethernet port, or multiple output links when that frame is to be forwarded on a particular segment. And so it uses that carrier sense multiple access collision detect, CSMA-CD, to access the segment. So it will probe the segment to see if anyone is talking on that communication medium. And if no one is putting energy on that medium, it will then transmit that frame on that segment. And it can do that for one segment or multiple segments. Ethernet switches are transparent. That means from the perspective of the link layer, all the hosts on network are unaware of the presence of switches. For all intents and purposes, they are invisible to each one of the nodes on the network. These Ethernet switches are so-called plug and play or self-learning. What does that mean? They don't need to be configured or programmed. And in that case, they're acting a little bit like a NAT box, but again, they don't deal with network layer constructs like IP addresses and ports. They deal with link layer constructs. And so switches don't need to be configured. They too are plug and play, just like how a NAT box is plug and play. Okay, so let's take a look at a typical setup. Here we have a switch in the center, and this switch has 1, 2, 3, 4, 5, 6 ports here. And each port corresponds to a particular network segment, and attached to each segment is going to be a network interface card, which is these green sort of cylindrical symbols here attached to each host. Now, each host is marked with its MAC address, and it doesn't matter what that MAC address specifically is. We do have host A and A prime, B and B prime, C and C prime. Now, hosts have direct connections to the switch, and again, this derives from the whole so-called hub and spoke architecture from the early days in the network, in networking. And these switches buffer packets. They're going to take these frames that come in, they're going to buffer them, and they're going to send them out some segment based on the MAC address. And so the Ethernet protocol is used on each incoming link as well as each outgoing link, but there are going to be no collisions, right? Meaning that there's going to be no multiple interferences, if you will, for the communication between, say, A and A prime versus C and C prime. And so what the switch allows is multiple pairs of communicating endpoints without collisions. Okay, so each link is its own so-called collision domain, meaning that there's no collisions between traffic that's going along one link versus traffic that's going on another link. And if there are no collisions, that means a larger proportion of the time will be used to actually transmit frame information rather than recovering from collisions, and therefore you're going to get much faster throughput when you have so-called switched Ethernet. Okay, and so for the switching, that means A can transmit to A prime, so this pathway can be established, and that means B can transmit to B prime, that means this pathway can be established, and they can do that simultaneously with no collisions. And so this particular switch has 6 ports, and you can go out and buy switches that have more than 6 ports and all sorts of different features and programmability. And I will show examples of these pieces of equipment in the next module on Tuesday. Okay, so this is a 6-port switch. So how exactly does that switch know the segment or the interface or port through which A prime is reachable, and likewise through which B prime is reachable? Now that pertains to this learning that we talked about. And all that is known are the source MAC address and the destination MAC address. So let's take a further look at that. So each switch, like this 6-port switch, has something called a switch table. And it's the switch table's responsibility to record information about what MAC address is reachable through which output port. And so in this particular case, this switch is going to have a switch table, and that switch table is going to have a bunch of entries. It's going to have an entry for the MAC address, and for that MAC address, it's going to have a port number or segment number. And so in this particular case, if you want to send a frame to A prime, well, the port that you go through is going to be port number 4. So then any of these hosts that sources a frame that wants to send this frame to MAC address A prime, once that frame reaches the switch, it looks up in its switch table, A prime, and then it forwards it out port 4. So this switch table acts a lot like something we've seen before. It acts a lot like a forwarding table or flow table in routers. And so each switch has a switch table, and that switch table has a bunch of entries consisting of the MAC address, media access control, for that associated host, and the interface, i.e. the port for that switch associated with the segment, the network segment, that collision-free network domain associated with that reachable host. And it looks exactly like a routing forwarding table. So the next question then is, how do these entries get populated, right? Is there something like a routing protocol? Well, no, not quite. It does learning akin to what a NAT box does. And so let's take a look at what this self-populating plug-and-play learning behavior is that allows a switch table to fill entries dynamically. So the switch learns which hosts are reachable through which interface, which port. And so when a frame is received, that learning process is associated with recording information for every incoming frame. So let's say we have a frame going in or sourced from host A. And that frame, there's a frame, is going to have a source MAC address. So that source MAC address, let's say it's trying to send this frame to A prime. The source MAC address is going to be A. The destination MAC address is going to be A prime. So when that frame is sent from A to the switch knows, okay, well, I just got a frame from source address A, and that frame from source address A came in on link 1. Okay, so with that, the switch table population system, if you will, that switch, it records the location, i.e. the incoming port number associated with that particular source MAC address. So in the switch table, that particular switch would record, okay, the MAC address is A, that's my source, and it came in on port 1. So if anyone wants to reach A, it's going to use port 1. Okay, so any subsequent frames that come in, if they have a destination of A, the first thing that switch does is it looks up in its switch table to see if there's an entry that corresponds to A, and it will know right away what particular interface or port it should send that communications out of in order to reach A. So it does it based on source locations. Okay, so we have a source A, destination A prime, and this is our switch table. Once it hits the switch, it records A as the MAC address because that's the source address. It records the interface on which that frame came, interface 1, and then also sets this third thing, a time to live field. Now this time to live field sets an expiration date so that the switch table will kind of clean itself up over time, right? After this time has expired in the TTL field, this entry is scrubbed. And so when it gets new communication from source A, then it'll repopulate it. And that gives you this plug and play behavior. It sort of automatically garbage collects. You can think of it as garbage collection. It removes stale entries. All right. So what happens when a frame is received at a switch? Well, the first step is you record the incoming link in that link entry, and you also record the MAC address associated with the sending host, right? So you have that switch table. You record, here's the MAC address portion, here's the link. You record the incoming link, so it came in on link 1, and you record the MAC address of the sending host. It was MAC address for host A. And then you index the switch table. You're trying to find an entry for that destination to know out of which port it should forward the destination. And one of two things can happen. Either you find an entry or you don't find an entry. If you find an entry, well, you just look up that entry and you look at that MAC address and look at the associated link and you forward out that particular link. If you do not find an entry, well, you're going to do flooding. And flooding means that you're going to forward a copy of that frame out of every single link associated with that switch. So if we had a frame come in here and there was no entry for destination address, say A prime, it's going to forward a copy or flood a copy of that frame out every single output port. Okay, and so let's see what happens with that so-called filtering and forwarding. The filtering part is the consultation of the destination MAC address, right, to figure out which link it should be forwarded out of, and then the forwarding is the actual forwarding along the link if the entry is there, or the flooding if the entry is not there. Okay, and then moreover it also records, right? That's called the filtering and forwarding. Okay, so let's take a look. Here's an example. Again, we see our 6-port switch. We have A prime, C prime, B, and B prime. These are all MAC addresses. So we start out, and A is going to source a frame and send it down the link to the switch. And initially, that switch table is going to be empty. So the source MAC address is going to be A's MAC address. The destination MAC address is going to be A prime MAC address. So A wants to send its frame to A prime. So it sends it into the wire. It hits the switch. The first thing the switch does is it records the source of that frame that came in on input port 1. It came in on port 1, so it records the interface as being port 1, and the source of this frame that came in on port 1 is going to be MAC address A. So now it's going to look up in its switch table to try to find a MAC address for A prime, and it does not find it. So what does it do? It does flooding. Now, when it does flooding, it does not send that flood message to the same port from which that frame originated. So a copy is going to get pushed out of every port except for port 1 because the source of this frame was from port 1. So it floods, so that means B gets a copy, C gets a copy, A prime gets a copy, B prime gets a copy, and C prime gets a copy. Okay, let me do that one more time. So this is our flooding. So now A prime sees this flooded message, and it sees the destination address, MAC address, is A prime. And it says, hey, wait a minute, I'm MAC address A prime, that's my message. So it picks up that message that it got from the network, and then at some point, it's going to send a reply. So then A prime sends a reply frame back to A. Maybe it's an ACK, maybe it's some other message. And the source address, the source MAC address for this message, this frame in the reverse path going back to A, the source MAC address is going to be A prime, the destination MAC address is going to be A. So this datagram, this frame rather, comes in through port 4, and once again the switch records, okay, well, the port that originated this frame is port 4, so it writes down interface 4, and the MAC address that sourced that message that came on port 4, the source MAC address was A prime, so it writes down A prime, and there's yet another entry. So then it does a lookup, and it says, okay, my destination is A, okay, let me look in my table, switch table, I see an address for A, interface 1, so I then forward that out interface 1 instead of flooding. So you notice here, if you get a match for interface for A, this destination MAC address for A prime, the destination MAC address, because you have a match in the switch table for A, then you're going to forward it out that link and not flood. Okay, and that's called selective sending. Let me say that again. Once you record that new entry in the switch table, you then do a lookup for the destination MAC address. It finds an entry for destination MAC address A is interface 1, so it does that selective sending, that forwarding out port 1 instead of the flooding. So you only flood, it's really important to remember, you only flood if you do not have a switch table entry for that particular destination address. Okay, so now you just send out one link and communication has been established. Any subsequent message from A to A prime is going to be forwarded across to out port 4, and any subsequent message from A prime to A is going to be forwarded directly out port 1. And so in the beginning, you pay the cost of flooding, but subsequent communications, you do not pay that cost of flooding. Okay, so these switches can be attached to one another and form something like this kind of hierarchy. So here we have 4 switches, S1, S2, S3, and S4, and we have a number of hosts attached to the first switch, second switch, third switch, and each one of those switches, S1, S2, S3, is attached through S4. So here's a question. Suppose you wanted to send from host A, so here's host A, and you wanted to, that's our source MAC address, and you wanted to send to destination MAC address G. How is this frame forwarded, right? Again, self-learning is going to occur, and it works exactly the same way as in the single switch case. So let's take a look at that. Well, it boils down to how the switch tables and forwarding occurs in each one of these switches. So A sources a frame, and that frame is going to have a source and a destination MAC address. The source is going to be A's MAC address. The destination is going to be G. So A sends that into the switch. S1 switch table sees that and records it. And I'll ignore the TTL field for now. And it says, well, it came on that port. So let's say that's port 1, 2, 3, and this is 4. And let's label them accordingly 1, 2, 3, 4. And let's label them accordingly 1, 2, 3, 4. And then let's also label this 1, 2, 3. And let's say 4 is not attached, right? Okay, so we have, let me adjust my headphones. Okay, so we have switch table for S1. And S1 switch table, it gets A through port 1. It gets this frame, rather, arrive through port 1, through interface 1. So it writes down a 1, and it writes down A, because if A source MAC address A came through port 1, that means source MAC address is on or reachable through port 1. So it does that, and it gets that frame, writes down that entry, looks up in a switch table the port entry for host G, it cannot find it. So what does it do? It floods. So it sends out that source destination A going to G out here. It sends it down here, sends it down here. It does not send it out port 1 because it originated from there. So now B and C get it, and they say that's not destined for me. I'm not G, and so they ignore it. But this one comes in from S1's port 4, and it goes into port 1 of S4. So S4 in its switch table, it gets that frame, and it has a source MAC address of A, and it came in on port 1, so it says port 1 if I want to reach A. All right, so it gets that, and it looks for an entry for G. It doesn't have one, so it does flooding. When it floods, it does not send out port 1 because that's where this frame came from, so it sends it out here. So here's my frame A and its source and G, and then it sends out that one as well. And that's going to have a source MAC address of A and a destination MAC address of G. So it sends it out port 3 as well. So now, of course, each one of these, AG comes here, S2 doesn't find an entry, so it forwards that through flooding down each one of these links. None of these machines have a MAC address of G, so they ignore the message. But this one that came down out link 3 when switch S4 did the flooding, it gets here to S3. S3 has a switch table, and in this switch table through port 4, it got this message where the source MAC address was A, so it's going to write down port 4, and MAC address is A. Okay, so it looks up in its switch table for destination MAC address G. It does not find it, so it does the flooding, and it sends out here that frame A as a source, G as the destination. It does the flooding here, does the flooding here. H and I say, oh, my MAC address is not G as the destination, so that's not me. They ignore it, but G says, hey, wait a minute, that's me. So G picks this up, and then it wants to send an acknowledgement. And if it sends an acknowledgement, G has its ACK has source MAC address G, destination MAC address A. So now this source G, source destination DSTA, it goes to switch S3 along port 1, and S3 says, oh, wait a minute, I got in port 1 something that has source MAC address G. So G is reachable in interface 1. Okay, so it writes that down, and then it looks up destination A. To get to destination A, I use port 4. So it's going to send out port 4 that source G destination MAC address A. So then that makes it to S4, and S4, oh, by the way, it floods when G hits the S3. It's going to flood, but it's not picked up by H and I. And it's flooded out here. That GA comes out there, and that GA hits switch S4. So S4 then through port 3, it got that source MAC address G. So it says port 3 MAC address G. It looks up the destination A, it finds A, and it forwards it out port 1. So it forwards it out port 1 here, and the acknowledgement frame has a source of G and a destination of A. So that's the source. That's the destination. It hits S1. The destination is A, and S1 looks up that A in its switch table and says, oh, go out port 1. So it sends that out port 1. There's my acknowledgement, source MAC address G, destination MAC address A. It says, oh, well, that's me. My destination, my MAC address is A, so I'm going to pick up this message and then display it or send it up the 5-layer internet stack. And so these are all the switch table entries as a result of sending a message from source MAC address A to G, and then the acknowledgement goes for source MAC address G back to destination MAC address A. Okay, so try this yourself, and the important part to remember that you record the entry based on the source MAC address. You then look at the table, look at forwarding table, or I should say more correctly, switch table, And then, after you've looked at the switch table, you do one of two things. You either forward selectively or flood. Okay, so it's really important to remember those three steps. Okay, so let's take a look at institutional networks. Institutional networks make use of switches. So here we have the individual switches in the bottom, and then we have another aggregating switch, and then we have a router to get that traffic off the local area network to the external network. So this might be your border gateway, for example. And so you have a bunch of servers. You have mail servers, maybe you have a web server, and then you have a bunch of hosts, and this might be something like a department or a division or some campus or some institution or enterprise. And so there's a difference between switches and routers. Both implement the store and forward function. Routers are network layer devices. They look at network layer headers. That's the IP address, the time to live, and so forth. Switches are so-called link layer devices. They only examine link layer headers. And so here we have a 5-layer stack associated with a host. And so the datagram is what we call it at the network layer. That datagram is encapsulated as payload once it gets to the link layer, and we add our link layer header information. We have the marching ones, we have the cyclic redundancy check, we have the source and destination MAC address. So that's what gets transmitted, the frame, through the physical layer, goes through the switch. The switch might do some examination of the MAC addresses and do that selective forwarding and filtering. And then that frame is then forwarded out, and it will go through, could go through a router along the way. Router then examines network layer, and that could forward along to another network segment or subnet to some destination up the 5-layer stack. And so they're both store and forward devices, but they store and forward based on different header information. Switches focus on link layer header information. Routers focus on network layer header information. They both have forwarding tables. In a router, the forwarding table is computed or calculated from the results of a routing algorithm. And that could be centralized in software-defined networking, or it could be distributed through traditional routing. So the control plane determines the forwarding tables that then get them into the individual routers, the result of the control plane action or computation. A switch does not compute the tables like a router does. It learns the forwarding using either flooding, this selective filtering, and forwarding and flooding. Right? So switches learn the forwarding table using flooding, learning, and the MAC address information, which are header information for the link layer, whereas the router does this computation, and we can have this either centralized through software-defined networking or distributed through traditional routing algorithms. Okay, so they perform similar functions, but they're not quite the same. It's really, really important to remember that. Okay, and so let's take a look at virtual LANs. When you try to aggregate traffic into multiple organizations, as you would have in an enterprise, all of this flooding and broadcasting and things like that, it presents a security risk. And it's very typical that you want to isolate all this broadcast traffic for one concern from other concerns. Think about financial information like payroll and things like that. And so you don't really want to have a so-called single broadcast domain, and there are multiple protocols that use broadcast. You have ARP, the discovery of MAC addresses based on IP address and building of the ARP table or ARP cache. There's DHCP that uses broadcast. Before you acquire an IP address, you broadcast your availability into the DHCP server that answers that. And so all of this broadcast traffic presents a security risk and a privacy risk, and you don't always want everybody, even though you belong to the same network, you don't always want everybody to have access to all the broadcast traffic. And so this idea of virtual LANs allows you to partition the broadcast traffic. So for example, in computer science, all the broadcast traffic for computer science might be separated from electrical engineering, from some other department like finance or computer engineering and so forth. And so virtual LANs or VLANs are specialized switches that are programmable. And what they're programmable to do is to associate certain ports with local area networks as if they were on completely different switches. And so there's so-called port-based VLAN, where you essentially can group the ports together and give them a kind of name, and each entity that's plugged into one of those ports in those numbered ports are going to behave as if they were on completely different switched networks. And so here we have a 16-port switch, and ports 1 through 8 rather, 1, 2, 3, 4, 5, 6, 7, 8, 1 through 8 are on one virtual network or VLAN, and ports 9 through 16 are on another. And so if you're in electrical engineering, you plug in all of your Category 5 or Cat 6 cable connected to your machines into port numbers 1 through 8, and likewise 9 through 16 would be for computer science. And so that means all the broadcast traffic associated with electrical engineering is never seen by computer science, and vice versa. And so switches that support this VLAN, or virtual local area network capability, can be configured to define multiple LANs using a single physical infrastructure. Now, this makes it a lot more manageable when you want to change things up. And so here we only have 2, but you could certainly have 4 LANs containing 4 ports. So maybe one VLAN would be here, one VLAN would be these port numbers, one VLAN would be those port numbers, and the other VLAN would be those. And this example just showed you 2 VLANs. Okay, so there are these VLANs operate as if you had more than one switch, right? So in this example, the first VLAN containing 8 ports, and the second VLAN consisting of the other 8 ports, it acts as if you had 2 different switches, each one of which would be an 8-port, but they're logically assigned to these VLANs using software, right? So it's much more manageable, and you can arbitrarily divide it up as much or as little as you choose to. Okay, and so you have this traffic isolation. You can also define VLANs based on MAC addresses of your endpoints rather than your switches. And in that case, you're not carving out blocks. You might say, okay, well, my first network, maybe it consists of the MAC address for certain sets of machines. So there, you're not kind of doing this yoga, if you will, where you're trying to divide up your ports. You're literally inputting a list of MAC addresses that you're going to associate as a single virtual LAN. And in that case, you can have arbitrary assignments of things plugged into ports, because you can have arbitrary groupings of MAC addresses for the particular interface cards for each of these devices. And so you can also define a VLAN based on MAC addresses of the endpoints rather than using the ports. And that's a much more flexible approach than carving up in terms of ports, because you can do more easily in software this assignment based on MAC addresses. And so in that, you can also have dynamic membership. Ports can be dynamically assigned to VLANs. And so if you're doing port-based, MAC address-based assignment, you plug in a MAC address that's in a certain group, regardless of what that port is, it now becomes a new machine in that particular group. And that gives you much more dynamism, the ability to change things, than doing it based on port-based assignment. Okay, now if you wanted to forward frames between virtual LANs, you'd need a router, right? And so you could either use a separate router, or many high-level enterprise switches will also come with routing capabilities embedded in them. And so they, honest to goodness, even though these VLANs are carved out of a single physical switch box or box device, these different switches literally physically act like different switches. And so if you want to get a datagram from the electrical engineering network, in this case, to the computer science network, you need a router to accept the datagrams from one subnet and push them out to a different subnet. And so in practice, these devices are combined. You have a switch and a router, and this is one such device that you'd buy from Best Buy for about $300, right? Okay. So you can also have VLANs spanning multiple physical switch devices. In that case, you kind of chain them together, and in chaining them together, you can treat that chained set of ports, if you will, interconnected set of ports, as if they were just one virtual LAN supporting device. And so here we have electrical engineering, and we have computer science, and maybe we have another switch that supports this chaining. And we have these special trunk ports that are specifically purposed with attaching VLAN supporting switches to one another. So in this case, port 1 of this right-hand switch is connected to port 16, and when you do that, it makes it look like it's one single big box that has the sum of all the ports of the left-hand side and the right-hand side switch. And so this trunk port carries frames between the virtual lines, between the virtual LANs, defined over multiple physical switches. And so in that case, you have 16 plus 8 ports, or 24 total ports. And this configuration, using this trunk port, it acts like a big 24-port switch instead of an individual 16-port switch and 8-port switch. Okay. So let's take a look at data center networking. And in a data center, the name of the game is density, right? So you have a lot of concerns like Amazon, Netflix, Apple, Microsoft, Google, and they traffic in tremendous amount of data, and therefore they host all of this on machines in a data center, of course, and they want to get as many instances of machines or as many processors as possible into a very small space. And so they build these data centers, as we said, closer to the beginning of the course, in specialized facilities that are specifically designed for this purpose. And so you might have literally tens of thousands to hundreds of thousands of hosts, and they're in very close proximity to one another. Now, part of the challenge of this, aside from the physical challenges like power and things like that, is managing all of the different applications that you might have. So let's think about what happens when you buy something on a concern like Amazon. Well, you're going to have a web server. That's a web server. You're also going to have a database. You're also going to have some sort of banking server that's going to be able to charge your credit card. You're also going to have something that's going to assess the taxes, right, if you pay sales tax. And then you're also going to have maybe something to pay the shipping, United States Postal Service, to get money to them if you're going to pay for that shipping. Or maybe it's some other concern. But nonetheless, you have a lot of different server-based applications that are interacting with one another in order to give you the experience of what it means to do electronic commerce, for example. So the challenge then is you have all these applications and they serve different numbers of clients, and each one is doing different things as part of the same process. So then the key question is, given that all of this stuff happens over a network, over multiple networks, with all the traffic isolation and the switches that are connected to one another, and the virtual LANs and the routers and all that good stuff, how do you manage all of the load, all of the interactions, these edges between all these different server instances? How do you do that? Because if you do it wrong, you're going to have a bottleneck. You might have some links, like let's say the link between the bank and postal service. Maybe that link to the bank gets so saturated that it breaks, right? And you don't want that to happen. So you want to avoid these bottlenecks by having redundant paths, and you also want to really think carefully about where you put these computations and where you place this data, because doing the wrong configuration can mean catastrophic results. You don't want saturated links, you don't want bottlenecks for data, you don't want bottlenecks for processing. Okay, so let's take a look at a typical data center architecture. And here we have a bunch of racks, and these might be typical 42U racks. So you'd have 42 units, each one of which can hold some number of processors or power supply and so forth, or storage array. And so here, each one of these 40 nodes in units in this 42U enclosure, they communicate very high speed with one another. They're not going a far distance, and they're often connected to a very high speed substrate through some switch. And that switch is called a top of rack switch, or TOR switch. Now this TOR switch accepts in an orderly fashion all of the Ethernet traffic from each one of these 42U units. And so communication from this first instance to the third instance to the 42nd instance, that's going to be relatively fast. And so all that traffic is going to be isolated, and absolutely you could carve it up into smaller sets of networks with VLANs and interconnecting them with routing. Okay, So we have this top of rack switch, and these top of rack switches are interconnected to one another with these so-called tier 2 switches. Now, when you think about what these rack enclosures are doing, you can organize your data center in many different ways. Maybe you have each rack being a specialist rack. So maybe this is all database function. Maybe this is all web server function. Maybe this is all United States Postal Service e-commerce function. Now, if that's the case, if there are a lot of communications between these separate concerns in your end-to-end workflow, you're going to have a lot of traffic leaving your Tor switch going up through the tier 2 switch down to another Tor switch into a different rack. So this is the case where there's specialists, each rack, specialists. Now, another organization you could have is you could have generalists. So as a generalist, let's say generalist architecture, maybe each rack has a little bit of each function. So maybe you have the web server, these are web servers in the process. Maybe the database, DB, these are databases. This is the USPS function and so forth. So you're going to have some traffic that remains within the rack interacting for some part of the process, and then for other parts of the process end to end, they're going to go to a different rack. So in that case, you're leaving that traffic local to a single rack, and then if you need to go and serve some other person, maybe you go to a different rack. And so this is a generalist approach, and the difference is you have all that traffic now staying local, but then once you go to the tier 2 switch, you're going to have a lot more aggregate traffic, whereas here it's less traffic locally, but you're going to do a lot of interaction to different racks through the tier 2 switches. And so regardless of the approach, whether your racks are specialists or your rack's functionality within a workflow is generalist, you have these tier 2 switches that then communicate your Tor traffic within our single rack between other nearby racks. So then you can take these tier 2 switches and you aggregate them even further with a so-called tier 1 switch. And these tier 1 switches are dealing with much more aggregate bulk traffic to get either inbound or outbound for the particular data center. Now, depending on the application that you have, for something like e-commerce, it's one sort of behavior for the flows, but in something like, say, movie streaming, Netflix, is going to be another type of application. Maybe each one of these racks serves up for a particular genre, or maybe it's different genres, but over different decades. Like maybe this is the 20s, the 30s, the 40s, the 50s for movies for all genres, right? So it all depends on how you choose to designate what each rack and each machine in a rack is purposed with. That's going to dramatically impact your traffic. And of course, when you're doing traffic engineering, you're really concerned with eliminating bottlenecks and also balancing the load so that one machine or one rack isn't working really hard while the other is relatively idle. You want to balance out the amount of work that's sent to each instance. Okay, so we have these tier 1 switches, and these tier 1 switches are connected through a routing infrastructure that ultimately leads to a border gateway, a border router, that then gets this traffic out to the internet. And so we also have other machines. We have the load balancer, and this load balancer is done through application layer routing. And effectively what this load balancer does, it collects statistics about how much work is being done on the various machines or parts of the data center, and then it farms out this work to different instances based on both the architecture as well as keeping everyone working as much as possible, balancing that load. And so the load balancer's job is to take that external request from a client and direct that workload based on some measurement criteria within the data center. And then it returns the results back to the external client, hiding the details of the data center implementation from the external client. So when you think you're connecting to Netflix.com or Amazon.com, what you're really connecting with is the load balancer, who's then farming out all of that work to each one of those instances, collecting the results and sending them back to you. Okay, so we have our request come in, and it goes through the routing infrastructure into the switch, hits the load balancer. The load balancer sends that off to some worker within the data center, some machine instance. It performs some work, and as part of that work, it might need to consult some other part of the data center. Maybe if you are a specialist, maybe you're the web server and you want to look up something from a database instance, and this might be the set of database instances. And so here, this red edge is the incoming request. This green edge is that collaborative work, so maybe you're requesting something, getting it back, and then you send that result back to the load balancer. The load balancer returns that back to the outside world, to your browser, and maybe that's you get your movie or your purchase is completed. Okay, let that run. So you want to have a rich interconnect between all of parts of the data center. And so you can increase the throughput and by having redundant pathways. And how you do that is by interconnecting another set of links between the tier 1 switches and the tier 2 switches. And so in this, if you wanted to get, for example, to this rack on the right-hand side, you could get there from this tier 1 to that tier 2. You can get there from this tier 1 to that tier 2, this tier 1 to that tier 2. And so you usually have rich interconnections among the switches and racks, and that increases your throughput because you have multiple or redundant routing paths between machine instances. And this tends to increase your reliability and your redundancy. That's both for outside traffic to make its way from the load balancer to a particular instance in a rack, or for traffic coming from a rack from one of the specialists, maybe to up here and maybe down here. Maybe this is your web server wanting to talk to your database instance as part of a workflow. And so you achieve scalability, redundancy, and reliability through this redundancy by having multiple pathways to get between arbitrary instances, be that from the outside world through the load balancer or between arbitrary instances within the racks. Okay, so with that, we will end there, and we'll pick back up next time. And this next time is going to be pretty short. We're going to talk about a day in the life of a web request, and we're going to use that as a framing example to tie up everything that we've been doing all semester. So with that, we're at 47 minutes. We will end there, and I will see you all on Tuesday. Thursday will be the exam. Good luck. I look forward to your answers on the exam. Please make sure if you have any questions, don't hesitate to contact me on the Slack channel, and I will see you all on Tuesday.